Okay, yeah, I can share. Yeah.
So it's a great pleasure to have Nir Gov as part of the SPL program, and Nir is from Weizmann University, Israel, and he's going to be talking about the oscillations using cellular directions.
Thank you very much. Just to say that I'm here for a sabbatical, so I'm here for the whole year until next summer, at least. So anybody who wants to meet me, there's plenty of time, and there's no hurry to grab me today. It can be tomorrow, it can be any other day of next week. So I'll tell you a work that started with a collaboration already almost 10 years ago with the people that you'll see in a second, and it deals with modeling in a very coarse-grained way one-dimensional cell migration. So the cell that is shown here is moving in one dimension or quasi one-dimensional like because it is confined to an adhesive line on which it can move, and any other side of the surface are non-adhesive, so the cell is confined. And if you saw the cell is moving in a sort of stick-slip way, there is a clear front, which is very active, with all this ruffling going on, and that's where actin polymerization is taking place. I'll speak a little bit about what's actin polymerization. Maybe I can... and the back seems to be not doing much, but from time to time you will notice that it is extending and then giving up. So there was an event here when the back seems to be trying to extend backwards. So there must be some activity there that's protruding, but it gives up after some time. So the person that did most of the work that I'll show you today is Jonathan, who did this as a PhD work, is now looking for his postdoc abroad, and Raphael Voiturier, which maybe many of you know, from Paris. And the work on the one-dimensional motility pattern was already published, and then there was a follow-up work where we teamed up with the group of Amrinder Naim, who is from Virginia Tech, who is actually studying specifically how cells are moving on these super thin 1D fibers. So again, it's a 1D-like problem, but unlike these works, which are on a 2D surface, only defined by a very narrow lane of adhesive substrate, these 1D fibers are really suspended, and there's nothing to hang on to around them. But still, the cells can walk on these tight ropes, and we show that the model can actually be useful to explain what they see here. The main part of the talk would be, after that introduction to the model, is how we extended that model to deal with this kind of dynamics, where a cell is moving on a 1D-like adhesive, 1D line adhesive lane, but then comes into contact with a junction. And all the junctions that I will show you today are symmetric Y-junctions, because they are the simplest for us to analyze. And symmetric in the sense that both arms are at the same angle with respect to the original direction of motion. If you have a square lattice, for example, and not a honeycomb lattice, then you always reach a junction and there's a direction going forward and two directions going at 90 degrees. So you might say that they are not all the same, because going forward may be more selected for than making a right turn, a 90-degree turn. So that would be already a directional decision-making where there is a bias towards one of the arms instead of the other. Here, there's no a priori bias to go either right or left. These are the only options. Or going back, that's also an option, and you'll see that actually that does happen.
So right,
yes, go ahead.
Yeah. Right.
Good.
What's the right spot?
So the right spot is probably the space called nucleus. Exactly. And there's another cell approaching from here, and we wanted to avoid cell-cell interactions. But when cells are seated on these surface, and they start walking on these narrow lanes, they do sometimes contact each other, and that is beyond what I will tell you about today, but we are thinking of how to extend it to that, to dealing with many cells working together, maybe even in connected clusters on such networks, which might be an interesting problem to think about, and we started to think about. You can see, like very typically, that this cell was polarized to begin with, that's why it was moving upwards, and therefore it has a very clear front and back, but after the splitting, it has now two fronts, so which are initially of equal strength, equal everything. So how to decide between them? And it's essentially the same 1D model, only now to describe the competition instead of being just between two ends, but now between three leading edges. Yeah, go ahead.
So when it hits the two angles, then it chooses for this case, it chooses the left one.
Yeah.
But then if you do the experiment again,
yes,
sometimes
there's no
you can
bias.
choose the
Yes.
right one, and eventually it kind of drags it along with it to one side, right?
Yeah, yeah. You see that? Yes, the cell doesn't split up, although it can fragment a little bit. Cells do fragment a little bit. They leave some small pieces, but not such a disastrous fragmentation that they die. And the other caveat that you have to see here, it's not so clear actually in this movie. Actually, that's a very good movie for us in that sense. Is that because the non-adhesive part, which is here, it can actually be bridged over into dimensions because there's no real barrier there in space. There's only a non-adhesive substrate. Cells sometimes actually go and cut across and bridge across these non-adhesive parts, which in the modeling will not be allowed. The modeling will be made out of purely 1D sections, which at a junction have to go through the junction and turn in each direction. So we cannot at the moment account for this bridging. Yeah.
Does the cell avoid each other in the sense
Ah.
that he's coming from?
No, I don't think that was statistically significant. They bump into each other as well, and sometimes they actually like to go where others have already gone because they leave like a slug. They leave something always on the ground. So that could actually form some biases that build up over time when they are walking many times. They could actually, at this particular junction, always prefer to go left because of some stuff that others have left there, and that messes up the experiment a little bit. We're now at the point that they are doing new experiments. I'll show you the people that are doing the experiments in a second, so they won't stay enigmatic. They're trying to actually now introduce controlled biases. So coming to a Y-junction and giving a controlled amount of small bias. You don't want the bias to be huge because then it's like a no-brainer. Of course, it will always go in the direction in which the huge bias tells it to go. But you want, for example, have a branch where there is maybe on the ground some chemical which is attractive to the cell, like a chemoattractant, but not in a diffusive form, but in a adsorbed form on the substrate. Or, for example, you could think of having an arm that has the same, let's say, maximal adhesion as the arm you came from, but another arm which is just a little bit less adhesive, but just a little bit, and to see how does that actually affect the migration. Okay. So this slide actually shows you again that we're starting with one-dimensional single migration, then there's collective cell migration on one-dimensional lines, which we're also working on, but I will not tell you about it now. If you want, we can have another seminar on that. And these are the junctions. And again, the junctions on this hexagonal or honeycomb lattice, you clearly see that when there's a lot of cells, you have interesting trains of cells like you had in this work by the group of Benoit Ledoux, but now on this honeycomb lattice. So this is, well, it's accepted, I would say, with some asterisks. It's not perfectly accepted yet, but it's, I hope, going to be, because we are getting good indications. Just to show you that this is not only physicists asking biologists to do strange experiments, it's also motivated by what's happening in biology. This is glioma cell, so very terrible cancer of the brain, and they are marked in green. And I hope you can see this is a brain slice of a mouse, and these are very thin blood vessels that, of course, permeate our brain to give blood to all parts of our brain. And these cells, they go on, they travel on these blood vessels, and you can see one arriving here at the T junction and then deciding to go right. If you look at it again, it will arrive from where my pointer is, reach the junction of the capillaries, and then decide after a little bit of some indecision to go to the right. So it does happen in reality. No, on the thin capillaries, on the outside of the thin capillaries. What's the time scale? Oh wow. It says here, so these are hours and minutes. Yeah. So this is yeah. I mean, there's another junction here. They're not perfectly like these nice Y-junctions, of course, but just to show that there is some relevance also in biology. So that's in a very thin slice of a brain taken from a mouse, and they can keep and they can keep it alive for even several days. I think. Yeah. So it's somewhere in between vivo and vitro. Yeah, ex vivo. That's a good term. I don't know if I need to go through what actin polymerization is all about, but it's highly confined to the leading edge of polarized motile cells, and it involves actin polymerizing near the membrane in a way that pushes the membrane forward and pushes all this mass of actin filaments backwards, because you can think of the polymerization reaction as a sort of pressure, a uniform pressure. And the actin which is flowing backwards is then sliding on the underside of the cell, which is here. And if it has some adhesion molecules that connect it with the substrate, then this motion, this retrograde flow of the actin is converted efficiently into a pushing force that pushes the object forward. So the final net velocity of this object is the most simple way to think about it is given by the balance between this pushing force of the actin and the friction force that this object has with everything around it, which is a little bit also the fluid, but mainly by dragging itself on the ground and breaking and reforming and breaking and reforming some smaller adhesion molecules. So the drag force equal the pushing force. Everything is in force balance. We are ignoring inertia, and therefore this retrograde flow of actin, the rate of it can be thought of equivalent or proportional, simply proportional to the net speed of the cell, and the proportionality factor is the effective friction coefficient. Yeah, okay. Yes, exactly. This is shown here. When actin is flowing backwards, this is the actin. It is actually being held by some adhesion molecules, and that's why its motion backwards is being hindered, and that translates to a much more efficient pushing force on the leading edge of the cell, which is being pushed forward where all the actin polymerization is happening. Okay, so the pushing force is proportional to this rate of actin polymerization, which is also proportional to this flow speed of the actin in the frame of the cell, which is the most relevant for us. So, yeah, we will consider, as far as explicit adhesion goes, only slip bonds which are important at the back, and they are shown here in this movie. So when the cell is moving upwards, you can see that there was a huge event of a detachment of this back of the cell, and that is thought to happen due to stick-slip behavior, which means that bonds which hold this piece of membrane to the substrate behave like slip bonds in the sense that they have an off rate which is increasing very much as they are pulled upon. So when they are being pulled upon, the off rate increases, and that can lead to a catastrophic detachment. I can show the expression of this in a few more slides. So the whole work started in 2015, shown here, and the idea was to take all of this complicated behavior of actin polymerizing electron and adhesion and convert it into the simplest one-dimensional model that we could think of. And the idea is to say that there is some chemical, which we do not specify exactly what it is, but it is a chemical that on the one hand can diffuse around in the cell and some of its time attached to the actin and therefore be transported with this actin flow away from the leading edge. So it will naturally be transported away from the leading edge, and therefore depleted at the leading edge and accumulated at the back of the cell. Now, in this simple-minded model that I will show you, we assume that indeed there is a constant and uniform, like conveyor belt of actin, which transports this molecule from the front to the back. It's not what really happens in the cell. There's nucleus in the center. There's other things which make the nice smooth actin flow only extend so far into the cell, and certainly not all the way to the back of the cell. But it's just a very simple-minded way of introducing the effect of the actin flow on how does it polarize the inner things in the cell. And again, what we call the concentration profile of this polarity cube, because we call this a polarity cube because it symbolizes what's the back and what's the front of the cell. It doesn't even have to be a small molecule. It can be even an organelle if you want. But anything that can both diffuse and can both be affected by the conveyor belt of the actin. And that work from 2015 gave the prediction that the persistence time of polarization of such a model will be exponentially dependent on the flow, because the larger is the flow, the stronger is this exponential depletion of this polarity cube in the front and its accumulation at the back. And it takes a longer time to spontaneously, due to noise, break this polarized state. It's like a double well potential with a larger barrier. And therefore the persistence time should go with the exponential of this slope. And that's what this semi-log plot is supposed to show me, that a lot of experimental data would actually be fitted to this expression. And that's why we call it this UCSP model, which is the general coupling between cell speed and the persistence. Yeah.
I have the cell membrane, and the cell is essentially moving. Is it possible for the membrane to kind of roll on the?
Okay, good question. I think so, but we don't go into that in the model. We don't have any of these details of the membrane in the model.
But in experiment,
I think it has to, but membrane at the leading edge is also doing some other stuff, such as transporting small vesicles to the leading edge in order to accommodate the extra membrane that you need in order to ooze yourself forward on the substrate. So cells are doing other stuff beyond only our naive expectation of just treadmilling of the membrane, like the tracks of a tank. Exactly. So cells are doing also other stuff beyond what we can easily imagine.
What happens when you watch cartoons with the sun? So
yeah,
sort of rolling droplets.
Yes. Yes, but the droplet has much less degrees of freedom than the cell, of course. Yeah. Okay, so that's in essence what I was telling you about. That we have this polarity cube which can both diffuse and be transported, and it forms this at steady state. It forms this exponential profile, which you can see depends on the net flow of actin across the cell and the length of the cell. So the length of the cell will be important, and also the net flow. And of course, the key assumption here in the model is that we have a separation of time scales, in the sense that we assume that the only dynamical quantity inside the cell that we will actually follow in our equation of motion will be the flow. So this actin flow will be time dependent, and we assume that this chemical has enough time to perfectly reach its steady state profile, which is given by this exponential, and follow therefore and be slave to the time dependent changes in the flow of the actin and the cell length. So the only dynamical quantities will be the cell length and the flow of the actin, and the assumption is that the flow of the actin and the cell length change on long time scales compared to the redistribution of this chemical across the cell. This is a very strong assumption. It immensely simplifies the analysis, of course, because otherwise you would have another equation of motion for C, which is given by this advection diffusion, and that would be horrendous to calculate everything. It will not allow you to get any analytical solution. So, but it's actually not such a real strong separation of timescales in reality. So we are walking a very tight rope here, which was motivated by the need to simplify the math, but in reality of the cell, these timescales are really not so separate, because the timescale for the actin to change its polymerization is tens of minutes, and diffusion of a small molecule across the cell is indeed faster than that, but it's not so clear in many cases. And for example, as I said, it has to be much faster than both the changes in the actin flow and in the cell length. And you saw that there are some stick-slip events where the back of the cell is making a huge change in cell length over a relatively short time. This is still not super fast, but it's faster than when the cell is moving smoothly. So during those short periods, this separation timescale probably breaks down, and probably this is not correct. That C has enough time to perfectly reach its exponential distribution. Yes.
I just want to check, is the polarity fused for something like myosin?
Yes, so excellent. So in the first work, we showed that it could be myosin, for example, which is transported in the back, and that's exactly what we want, which I'll show you in a second, which is feedback onto the flow, because all I told you is that this polarity Q is affected by the flow, but the key point of the model is that it affects flow in turn, and that completes the feedback, and that gives us the spontaneous polarization of the cell. So myosin was the first option, and that was the main thing that I had in mind, but actually the referees of that original Cell paper wanted something else, and thankfully at that time in Paris, Alexei, I don't remember his last name now. He worked on ARPin, and ARPin is a molecule that actually does inhibition of actin polymerization. So it inhibits ARP3, and it also binds to actin, and we could show that it actually is depleted from the front. So it can serve exactly as another molecule. So it doesn't have to be myosin. That's what I'm saying. But myosin is, of course, a big choice. So the key point is to connect the flow back to the concentration. And the assumption was that this molecule, this polarity Q, can be an inhibitor of actin polymerization, for example, like the ARPin. So what you now have is that as actin is polymerizing more at this edge of the cell versus the other edge of the cell, you get depletion of this molecule from the front and accumulation at the back. The front polymerizes now even more strongly, and the back even less so. So the asymmetry between polymerization in the back and the front grows, and therefore the net flow increases, and you can get a positive feedback that under the right condition can lead you to a bifurcation. What are the necessary conditions? Well, basically all of the parameters have to be right. But for example, you can just play with length, and you can see that when the cell is too short, you basically don't have enough length on which to build this asymmetry of this exponential. So you cannot self-sustain this polarity, but beyond the critical length, you can actually self-sustain this polarized cell. So the cell has a mechanism of self-polarization, of spontaneous self-polarization, and that's the key to everything that I will show you next. So the first thing was to take this model and now make length also a variable, because in the original Cell paper, the length was just a parameter. But clearly, we want to explain stick-slip behavior over cells elongate and shrink, elongate and shrink. We must treat the cell as an elastic object, minimally an elastic object, maybe much more complicated than a simple spring. And the key point here is that also the adhesion at the back, which is depicted by these blue springs, has this slip bond behavior. So you see that the off rate, which detaches these ends, which ends are the attached bonds, goes like the force which falls on these bonds, and the force which falls on these bonds is basically the pull of this spring because the cell is moving to the right. The right is the front cell, the front part of the cell is trying to move. The back is being pulled, and you get all of this elastic force falling on all of, shared by all of these attached bonds. And that's why it becomes catastrophic, because as soon as you're beginning to detach and becomes small, and then the whole force is now shared by less and less bonds. So it just has a runaway tendency, and you completely extinguish N. So it's like, and then it has to rebound. Yeah.
That's also force feedback.
Of the bond or the model?
The molecules which are the molecules which are essentially there in the model.
That might be, but it's not included here. It's not included. Yeah. So we have several parameters. R is the stickiness to the substrate. We have the elasticity of the cell. And for example, in this simple model, we could show that you can start with very weak adhesion to the substrate. And let's say you fix the elasticity of the cell, and you get the cell moving smoothly and fast, but it's very short because there is not enough adhesion in the back to elongate the cell. Then you crank up the adhesiveness, and you go into this fixed behavior, and you can see now the chemograph of the cell, and you go into this limit cycle of cell length versus strength of the adhesion, and you can see that periodically the adhesion in the back completely collapses as the back is making this shooting motion forward. And then if you crank up the adhesion even more, you go, there's a small region here of stability, but you go back into smooth motion. So there's not any more stick because the back is sticky enough so that you never deplete them so much that you get this catastrophic event. But now the cell is very long because there's such a strong adhesion in the back that you're elongating it, but it's stable. So it moves smoothly, but very slowly because you pay a price for this strong dragging in the back. Okay, so everything is clear. And then, of course, these smooth motions will be like a stable point here in this phase space. Then, the full model that eventually we had was that the length is variable, the adhesion is variable. That's this slip-on, but also we don't want to specify a priori where the cell is actually going. So there is actually a local polymerization activity which is happening at each end independently of each other, and they are linked to each other through this inhibition. And the next flow is simply throughout the whole cell is simply the difference between how much is polymerizing in the front minus how much is polymerizing in the back. So this complete model gives us the fact that if you are starting off with a very short cell, it will elongate as long as it is in the below a critical length. The elongation is equal on both sides because there's polymerization here and here, which is pushing the two ends apart until you reach a critical length, or you don't, depending on how strong is your spring which is resisting this. And then at this point, you break symmetry, and the front becomes with high polymerization, the back becomes with low polymerization, never zero, but low polymerization, and then you go. So then the cell has broken symmetry spontaneously. And you can calculate what's the critical length, and you can calculate also what's this critical length, where you can still balance the forces because of the stiffness of the spring.
So going back to your initial videos,
yeah.
What you saw at the front, the symmetry was really very strongly broken, and there was ruffles at the front, and the back looked relatively quiescent.
Yes.
Yeah. So,
but it's not perfectly quiescent. In fact, if you look at the chemograph, you can actually see, it's actually clear here, that the back from time to time is not actually making pure stick slip, which would be to go like this and then like this, but it's actually growing backwards. And this growth backwards means that there is actin activity there. protruding backwards, losing eventually, but there's true acting polarization going backwards. And the only way we can explain that in our model is to say that we are not actually in this regime of pure stick slip, so that we are constantly making it stick slip, but wherever we are, even after the slip event, we are above the critical length. But no, we actually have to go, we have to actually, after each such catastrophic slip event, go slightly below the critical length, such that in fact the cell tends to reach polarity and therefore grows now equally on both sides. And that's the only way we can explain that phenomena that you saw in the graph. It's not perfectly that it loses polarity, because you can see that it underwent many such events and still it always goes in the same direction. And the reason is that it takes some time for the internal flows to adjust to the change in length. And if we make this time long compared to the noise, for example, then they will always regain polarity with the same direction, because they didn't lose memory of the previous event. But if we make this memory or time it takes for the velocity to adjust after length changes fast, or alternatively simply increase the noise, then you see that it's just flipping of the coin after each such event, whether you make a complete reversal of your direction of. So it seems that the first movie that I showed you is in this regime, where you grow initially backward, you give up, again backward, you give up, but you're maintaining your polarity in the same direction. You're not flipping the coin after each event. So it's in this regime of noise versus time it takes for the velocity to adjust. Yeah.
The upper graph retains the dynamics of this chemical cube that
Yeah.
has to adjust. On the right.
This one?
Yes.
So the chemical cube is sort of adjusting instantaneously. But what takes time here is for the acting polymerization to readjust to the changes in the polarity cube. The polarity cube changes instantaneously. That was the simplifying assumption. Okay, so yeah, and then I mean, if you look up this PRR paper, we compare. I mean, this is of course a little bit anecdotal, but you can see again this growth backwards, which you can see here, but you maintain the polarity. Of course, you can have all kinds of, I mean, cell divided here, and you can try to fit nice chemographs to everything. Maybe I'll skip this part because of the work with Amrinder on the fibers, and I'll get to these junctions, which was the title of the talk. But you needed to understand what is the model first. I apologize. So basically, what we did here is did exactly the same model that I showed you before. There is a spring which now connects all of these independent ends. So basically, we now write the same set of three equations of motion, but now to not just two ends, but to three ends or even more. You will see later, and repeat the same story where they compete by the fact that the one that polymerizes the most strongly pushes this inhibitory polarity cube against the other. But now it doesn't push it only against one back, but against two backs. So and the data comes from Pablo Saiz from Hamburg and from Neil and Pascal in Milano. And Gi was an excellent undergrad student who started working with me by Zoom while the Corona pandemic was on. And she just now started her graduate school in Yale. So we should wish her luck. She's really excellent. Yeah, okay, so that's the phenomenology. You saw that before. Just to tell you that many people are looking into these kind of questions, how cells make decisions, but these I think are much more complicated to analyze. What they tried here is various channels of different sizes in order to see what happens to the nucleus in particular as it tries to squeeze. This is again a square lattice with high density, so it makes it much more complicated to analyze. And also, as we said, there is an inherent bias where you go. So we went to this. We asked them to go back to honeycomb and also to increase the size of the honeycomb to begin with, such that the cell doesn't actually spread, even though it's just an elongated cell, over more than one junction at a time, which actually can happen if you don't correctly fit the size of these hexagons to the size of this stretching cell. And that again makes it more complicated. I'll show you that we are now actually there. We can explain the cell spread on more than one junction. Okay, so the model, if you remember, had that the flow from one edge is pushing the polarity Q to the end. So we said for 1D line that it's basically the flow from this one versus the flow from this one, whichever the one minus the other gives us the net flow that affects this polarity Q. Now, what happens when there is the junction? So we did the simplest assumption, and again, it can be open to criticism, that the flow is simply split into the two arms as it comes. So when I'm polymerizing here, within this arm, the polymerization strength that comes out of this arm is fully given to the advection of the polarity Q until this point. And from that point, the flow that comes from here is split into these two. And the same goes for the other, equally. Now, we might have to do that unequally when the angles will be different, and that's exactly what we're thinking of. But how? What is the rule? We don't know. So, something like that, for example. Yeah, exactly. So this is simple. It's just equal. And then everything is solvable as before. And already we found something super surprising. And the surprising thing, it can be shown in here. So we take a cell in the simulation and we place it on the junction and let it grow equally in all directions. So if you look at the length versus time, first of all, if the activity is below some critical value, it will just grow, but all of the arms will have the same length and they will be lower than the critical length, which is here, and it will just stay as a star and not move anywhere. And you can see here, that's the elasticity, that's the maximum polarization strength, which is better. And you can see that below a critical polymerization strength, which is given by this line, cells will just remain trapped on the junction and not move. And it's actually interesting because there is also a critical beta to start moving on the line, but the critical beta for getting untrapped from this is higher, which means that you can actually move very nicely on the line, reach the junction, and get trapped there just because of geometry. Just because the fact that your active polymerization machinery and this inhibitory tube is now spread along three arms, and all of them are competing, and you cannot make a decision. So there is actually a regime here where you can move perfectly well and polarize in one dimension, but reaching this junction, it's a trapping, although there's no real trapping potential, only because of this. I'll show you. And above that, this is only the theory for the moment. Above that critical line, you can actually have this seesaw mechanism that I'll show you about. And even above that critical line, you have two effects which will be interesting. You have a fast decision, which is called the fast process, but a new process which comes about, which is actually super slow, which is strange because you actually cranked up the activity. So you are supposed to move faster, and along a single line, you are moving faster. But a new, slower process is actually coming into existence. So if you are above this critical line, you look at the simulation. You are growing equally, so all the lines of the different colors that symbolize the three arms are on top of each other until you reach a critical length, which is reached by this LC. And then you see that one is already the loser, the green one, but the other two are still undecided between them. And eventually, they also make a bifurcation, second bifurcation, and the blue is the absolute winner until the other two just wither away to zero, and you leave the junction. So this cell was spreading on the junction, not sure where to go, and eventually decided. Now, what's interesting is that you see that while the green was shrinking after it was designated to be the loser, it starts growing here again. While then it starts going down again, the red is slightly not shrinking anymore, but it's very difficult to see it in the length because the length is just the integral of these forces. But if you go to the differentiation of the length, which is actually the forces which are pushing the edge, you can see dramatic jumps here. So this is the actual calculation of this flow or this polymerization of actin at the edges of the arm. So initially they're all the same, but when there is the first bifurcation, the two winning arms jump in polymerization because they're able finally to push this inhibitory Q against the poor green arm, which is losing. But then when there was a second bifurcation, look what happened. The green actually recovered its polymerization strength almost as much as the winning arm. And one of the arm which was the second loser is now shrunk. And then there's another such oscillation until the two of them completed our way. And this oscillation was surprising to us. The word oscillation is maybe a little bit misleading because it's not, there's no limit cycle here. This is a one-way ticket until you leave the junction. So we called it more like a seesaw oscillation because it's more like a few rounds of the seesaw and then it finishes. And you can actually do a very interesting analysis. I don't know if I have time to describe it all. But that what Jonathan did is that he took a few times here at the just before and just after these oscillations, and what he plotted are the solutions for the flow in arm number 2 and arm number 3, which are the two arms which are those that are oscillating between each other, the green and the red. And you can see that just, okay, what is the x-axis? The x-axis is actually the length of the winning arm. So what he said is that at this time, the winning arm is constantly growing at almost a constant rate. So let's just use that as a parameter, and we'll fix the ratio between the length of L1, L2, and L3 as we measure from this numerical simulation. But now fix that and now do an analytical calculation for what are the branches of solutions. And you can see that just before this oscillation, the red one has a solution which is up here, and just after that, because these dashed lines are constantly moving to the right as L1 is lengthening, you cannot stay on this branch anymore, and you have to move to the other branch because that's the only branch that now appears in your length, and you have to therefore jump to the red branch, and you jump all the way down here. And the opposite happens to the green because it was following the dashed branch, but that branch is constantly shifting to the right, and now there's no point anymore. You have to drop off it, and you jump over to the other branch which exists in parallel. So you can follow these solution branches, but maybe I can also explain it more intuitively. And intuitively, you can think of it as follows: as these two are lengthening, and this one is short, you know they are much stronger, and they push all of the inhibitory Q on it. But as time goes by, this becomes long, and also the red becomes long. So you now have that the longest path in the system is not anymore from the red and blue down to the green, but actually from the blue to the red. That's actually a longer path in this system. And the most stable situation, or the most stable situation for this system, is to always have this inhibitory Q being dragged along the longest path, because then you can actually form the strongest exponential difference between front and back. So you can intuitively understand that it has to happen, because as the red and blue are both lengthening, at some point along them, and not along the poor green one, which is shrinking, you actually have the longest path. So the system becomes unstable and switches over to the next stable solution, which is now to inhibit red. I mean, blue is not likely to inhibit because it was always chosen to be slightly stronger, just by chance numerical noise to begin with. And therefore, this has to happen. So it's a deterministic oscillation. There's no noise here, right? So there's zero noise in this calculation. Okay, so it's not a limit cycle, and it's not oscillation because of noise. It is deterministic, and it has to happen. And it's not an oscillation. It's more like a seesaw event. You can see the same kind of oscillation, but maybe not 2 or 3 rounds, but in this case only 1 round, when you actually now not spreading your cell on the junction, but allowing it to arrive at the junction, which is more the realistic state in the experiment. And now again, if you are below the critical beta, then as I said, you can actually be moving very nicely on the 1D line, but lose polarity and get stuck on the junction. But if you are above this critical beta, you have the back which is shrinking, the two new arms which are growing. At some point, there is the bifurcation. One grows and the other one shrinks, and they all shrink away. And you see that there is oscillation in the sense that the red, which was one of the new arms, loses its polymerization strength, but the back suddenly recovers its polymerization strength before they lose. There's another small oscillation here, and then it dies away. Yeah, there's another kind of type of oscillation which sometimes happen in the beginning, like these very, very quick oscillations between the two losing arms before you set into these nice large oscillations that I talked about before. So it's quite a rich and nonlinear system. So how can we compare this to the experiment? So the experiments look at the cell which moves here in this movie. And it has to make a decision. And you saw it wanted to go first to the left, then it made even maybe a way back, but eventually it went to the right. So this is the traces, these are the traces of the arms from the experiment. And how would we measure the local acting polymerization? That was a very tough thing to do. So we looked at two proxies for that. We took a finite window of distance from the tip of each arm backward. And we said, let's look first at the area of this region, because if there's a lot of polymerization activity, there's a lot of lamellipodia, the area will be large. And also we can look at acting fluorescence. So you can see that's the tip intensity is the amount of acting fluorescence at in this window, which is a certain 10 microns or so behind the absolute tip, and the area of this region. And we plot that, and that's the simulation. And what we wanted, and that's also the simulation traces and the polymerization activity. And what we wanted really to look at is cases where we could see that when one of the losing arm goes down, the other losing arm goes up. So you can see that there's like this anti-motion here, and there's a single oscillation here between the red and the green. There's another example here. So I think this one was glioma. Yeah, these are the glioma cells. This is the UVEC cells, which are not cancerous. And again, you see the cell coming from the top in this case. There are some oscillations here. It even maybe wants to go back a little bit, and finally it makes a decision. And again, you can see an event here where the green polymerization goes up, the red goes down. The red goes up, the green goes down, and then the green goes up, the red goes down. So it's really the activity at the tip. It's not the length, right? Because the length is something sort of easy to sort of think. I don't need all your complicated model. If I'm pulling here, I mean, if one is pulling strongly here, the others have to pull back. I mean, that's simple elasticity. But the activity of the polymerization at the edges, that's the big oscillation that we predict here. And of course, it also affects the length, but to a much lesser extent. You see, the lengths do oscillate, but it's more these oscillations in activity that we wanted to point the attention to. That's, again, this movie that we saw from the brain slide. So that's the experiment, and that's a sort of simulation that was fitted to look roughly similar. You can see a stick slip event here in the simulation. Maybe this is not exactly the regime of the experiment. Just to show you the final type of behavior, final types of behavior that we found here is that if you look at the mean time to go across the junction, you reach the junction, how much time in arbitrary simulation units it takes you on average to cross the junction. As you crank up the acting polymerization activity, not surprisingly, this time goes down because you're just a faster moving cell. So you also go across the junction faster. But above a critical activity, there seems to be a sudden jump in this mean time. And the reason is shown here in the distribution of times it takes you to cross the junction. When you are at this high activity, there is a certain peak of events which are very fast, and they are not surprising. But there's now a large distribution of escape times which are orders of magnitude slower, in this case 10 times slower. And the reason is that because you are such a strongly polymerizing cell, you are growing the two new arms so quickly that you reach a situation where this arm has shrunk to zero. It's really zero. You can see it here. This was the green, it's now zero, it's completely zero. And the two new arms are of equal length, they are so long, they are so strongly flowing all of this inhibitory Q here, that they are almost at the same length until at the end, this is resolved and one of them wins. And this is the traces from this movie, which shows a similar behavior, but you'll see that at the end, the cell actually resolved it in another way, which I hinted to in the beginning, and maybe you can already guess, and that is to bridge over the non-adhesive substance. So it gets stuck like that for a long time until at some point it just gives up on the junction. But still, it has still to resolve this indecision, and eventually one side snaps. So it's not exactly resolving it like in the model, because in the model, this part of the touching from the junction is not allowed. Okay. So in this experiment, it wasn't actually looked at, but I've seen recent work that was described in some conference where they said that they showed a movie where you can see that on such junctions, you can see the nucleus going to the right, for example, and you say, okay, so the right was selected, but no, eventually it went to the left. So it's not where the nucleus goes that the cell will go. You cannot say a priori. Okay. Just to show you that from our prediction, we say that faster moving cells should show more of this slow process, and indeed the UVEX show a slower escape time, but it is rather uniform, while for the glioma cells, which correspond to faster moving cells on average and larger beta in the language of our model, indeed there was a distinct occurrence of these much slower events compared to the mean of these cells. What's the effect of noise? And that's the last effect I will show you. The effect of noise is actually the following in the model. If you have low noise, you come across a junction, you have a distribution of escape time, and whether you go to the right or the left, so red or green, is equally likely. Of course, there's no bias. Now you crank up the noise, and what you find is that you have now a more complicated distribution of escape time, and actually there's now a peak. So there's still the fast processes which don't distinguish between going right or left, but there's now slower processes where you have a high probability of actually going in the back direction. So the blue trace is actually the trace of probability of going in the direction of the original arm you came from. It doesn't exist here, because here there's zero chance of going back, but here the noise allows you, and actually you are more likely to reverse for these processes than actually go forward. And you can actually see such events. So a junction, which is strange because it offers you more directions of going, because of the indecision, makes you go back. And you see this cell, it didn't know where to go, and then the back eventually said, okay, you can't decide, I'm taking over, and it went back. And so it's a slower process than just going straight through, but it can happen if the noise is large enough. If we crank the noise even larger in the model, then basically you lose when you arrive at the junction, you lose memory of where you came from. And now you see that you can leave the junction equally likely in all three directions. So all the three traces are equally likely at a third. And you have basically an exponential distribution of escape times. And this is what's shown here. This is an experiment of a cell that was actually trapped for as long as the experiment went on in this junction. And you see, it almost makes a decision, but it never actually makes a decision. And you can get a similar simulation in this regime where the noise is high enough. You can see that now the escape times are orders of magnitude longer than when they are for low noise, for the same system with low noise. And of course, we don't know exactly what is the right noise for the cell. But you see, this cell just never makes its mind up. It goes on and on and on like that. So yeah, so trapping and reversals, we talked about that. There's a few more examples here, but maybe time is running out. I'll just tell you that the referees asked us to do some drugs. So for example, you can add latunculin, cytocalastin D, or blebistatin. Latunculin, in the simple language of our model, basically inhibits down the polymerization in the front, so reduces this beta, which is the treadmilling of the actin. Blebistatin kills myosin 2, which does many things, but maybe in our model basically reduces the contractility of the cell, so making it a much softer cell. And cytokeratin D disrupts the cortex of actin, so maybe reduces both the polarization of beta, but also softens the cells to make K smaller. And these are shown here, at least qualitatively, by the arrows, levistatin, latrunculin, and cytokeratin D. That's the model prediction. And you can see what happened in the experiment. So, for example, if you look at latrunculin that inhibits beta, so what happened in the experiment, the length of the cell became shorter, the velocity became smaller, and of course the escape time to the junction became much longer. And that's exactly what you predict from here. So if you move in this direction, so you see that the length the length becomes smaller, and the velocity becomes smaller, and the escape time becomes larger. So at least qualitatively, we can explain all the three drugs. What happens when you move on a real complicated network where your cell can actually span several junctions at the same time? We're already there. Basically, we extend the model, which I showed you in the talk, which dealt with a single junction, to the same object, but now spanning many junctions, as many as you want. The only problem we didn't actually put in yet is what happens if it completes a full circle and touches on itself. So we haven't done that yet. So we don't allow that in the simulations yet. But of course, that can easily be added. And now you can ask, how does this object chemotax across a network like that? And all kinds of questions of that sort. That's another motivation that I found very recently on the internet. It's these Langerhans cells, which are being studied by this lab in Seattle. And they have this on their website. It's beautiful cells, which now all these dark spaces that you see here, these are all skin cells. So what you don't see labeled, all the dark matter here is full of skin cells, which are super tight in your skin, and in between them you have these super flexible cells which are constantly patrolling. They are a kind of phagocyte, eating up debris of dead cells, etc. So you can see how ramified the structure here is, and if they need to move towards something important, maybe we can capture their behavior with these behavior. And of course, here you have oscillations. As you saw already, some of the oscillations can be driven by noise if you crank the noise high enough, but there's also something here which is deterministic oscillation, which I think is very interesting, and it's easiest to see it not on this complicated system, but on the single junction, of course. So yeah, that's yeah, thank you.
This one, is it 2D or 3D?
So this it's in vivo. So it's in the I think, if I'm not mistaken, the vivo, if I'm not mistaken. And I think because of the skin naturally forms layers of cells, it's roughly 2 dimensions. Yeah.
If we are migrating in the junction of the cell?
Yes. So all of these regions here, you can see it nicely in their paper, where they label both these cells and the skin cells. They don't form a perfect hexagonal network, but they form a very tight network, and these guys just stand out there, protrusions in between those cells. They are also migrating. They are not only just making this dance, they're also migrating. But more strongly, of course, if there is some cue, if there is some damage. They are especially apparently specialized for eating dead neurons. I mean, we have skin, we have neurons in the skin for sensation, and these neurons apparently undergo a lot of damage and breakup, like everything in the skin. And these guys eat up the debris. Yeah.
Any other questions? So I mean, these things are they have any collective behavior of use and collective behavior of these cells? So that, like another here where
they don't,
where you have more than one cell following.
These are specifically, I think, rather individualistic. I'm not an expert in them. Maybe I should have stopped in another slide. All the questions are about these Lagrange cells, but I came across them just because they're so beautiful. Maybe we should look more at these cells because these come from Pablo's lab, and you can see that these are macrophages. And basically, what he did is that he used the same hexagonal network that I showed you before, but on a smaller scale. So now this cell is actually spanning several junctions, and we are trying to compare this data to our modeling, which has been extended by GI to several junctions, to many junctions. Yeah.
Sorry, did it cross the random walk or?
So it's a good point. Okay, so in the model, at least as far as we looked at, but we haven't maybe looked at all the regimes. It looks like that on large scales it is a simple random walk with an exponent of 2. We were thinking that maybe because maybe that's true, that if we are entering regimes where they get trapped at junctions, and in fact, as I told you before, that you can actually be in a regime where you move perfectly well on linear lines, but you get trapped on the arms. The critical beta, the critical activity that we need in order to make sure that that doesn't happen is even more restrictive when you are on spanning, let's say, 2 junctions and 3 junctions. So you can be in a situation where you are not trapped on a single junction, but if you span 2 junctions, you get trapped, and so on and so forth. So if we are in that regime, this is not the case because this clearly doesn't get trapped, then we might get interesting random walks because we will get now some effect of the trapping time distribution. But again, if the trapping time distribution is itself a simple exponential, we'll go back to on the long scale to normal diffusion and nothing abnormal or subdiffusive or anything like that. But we haven't checked that yet because of the issue of the trapping that could be interesting. Yeah.
Okay, maybe this is now a bit that field. Just generally, this is more about utility. And when you are going away from 1D, thinking about, let's say,
open space.
Open space.
Yeah.
Because I guess that there's also, I mean, I wonder whether one can start thinking about how it makes decisions, how you make decisions in this more complex environment. Because presumably, in the end, I mean, here, one thing, nothing is 90, but basically, it's only you have 2 choices. Presumably, then you try to think about it in 2D, then you'll have essentially some kind of continuous field to define the direction. But maybe want to go to use similar arguments to talk about what would happen if such a thing came to have to make a decision.
So it's exactly in the direction where we're going, where essentially what we try to do, what we are doing at the moment, and we're still playing with it, is that what I told you is that we have a 1D model of the cell where you have activity here and activity here. But what would happen if you now have a circular cell and you have activity everywhere? So we call these Motile units, which are simply distributed circularly. And now, in order to polarize this object, because of course, if all of them are on or off equally, then it's not moving anywhere. And this eventually had this transition to a polarized state, which is persistent. And then it doesn't anymore just make random noise, but it's making persistent random walk. So can we have this in 2 dimensions? That's exactly what we are looking at. And you can actually say that in a simple-minded way, you're now summing up all of the local activities into one single net flow in the system, and then you basically map this inhibitory signal along this single axis, and if that feedback is now strong enough, lo and behold, this will also begin to be polarized. So that's something we are right now looking at, and then you can now look at its motion in 2 dimensions, and whether you can have regimes where you can have, as we said, something which is beyond intermittent random walk, something which is more like Levy flights or something like that, we don't know yet. But about decision making, that's actually interesting because now you can say, okay, what's the decision making in 2 dimensions? So what we thought could be an interesting decision-making problem in 2 dimensions, we don't want to use any geometric confinement because then
we have two cubes.
exactly. So what we have at the moment is an idea to test what happens if you have 2 or even more local signals for chemoattractant. And now you can say that there is some field which decays away from this source, and depending on where I am on this cell, I get enhanced according to the local concentration. So there's more likelihood to be on if I sense this cue, but there's another cue coming from there. So what will happen here? And what we have not done that yet, but what I would like to see is something which is a little bit like this spin model that we did for directional decision making of an animal, and in that work, which was shown to agree with experiments on animals in virtual reality, is that not surprisingly, you can, if you're very far, you just move along the compromise between the two of them because the angle between them is too small, but there is a critical angle beyond which there is a bifurcation. Now that by itself is trivial, but the nice thing of that work, which I would love to see also on the cellular scale, would be what happens when you have 3. And what we found for 3 is that again, when you're very far, you are the compromise of all 3 of them because the angle is too small. But then you reach a critical point where you make a bifurcation where you give up, let's say, on this edge one, but you're still undecided between these 2. So it becomes a hierarchy of decisions, of binary decisions. And that's what we found for the spin model for decision making of an animal or animal group also, and was corroborated in experiments on animals. So maybe that could also happen on the cell level of the single cell. I don't know, but that's where we're exactly working on. Yeah.
I vaguely recall work on equal stealing, so the fact that the sensing of gradient and the ability for the collaborators. So any relation to this? So they of course have this sort of strong nonlinearity level call that thing. And there was some notion that the question is it that the P wave mode dominant, but depending on the size of the cell, or can I have to multiple folds with all these?
So
I'm not entirely sure.
in this simple-minded picture, it won't happen. In this simple-minded picture, we'll have a single fold. But it's because it's limited to something so simple. In reality, a cell can have multiple folds.
Well, if you just decrease the use of length,
Yes.
it becomes more local, and that's not that local like this.
Yes, you're right.
Which you may have.
Yes. Yes.
So can I ask you
Yes.
a question? Very, very basic, going back to the thought.
Yes.
So you explained the symmetric reference rate and flow in run in the frame of the cell.
Yeah.
And then the question is, what is the flow velocity relative to the velocity of the cell?
Yeah.
And there was proportionality.
Yes. Yes.
What is proportionality constant? And I thought you had some slide somewhere showing that the 2 velocities are actually equal in
They're proportional to each other.
but I thought they were actually equal in wild type. Maybe I didn't read that peculiar figure. I think maybe the previous slide or yeah.
Yes.
So what is happening there? Actin slip.
So this is an experiment. Yeah, so this is an experiment where they play with the adhesiveness of the substrate. Right. And what they can show is that what is important for the persistence, which is shown here, is the acting retrograde flow in the cell frame, which means for the cell frame, you have to add the measured acting slip speed that you are measuring in the lab frame, plus the cell speed in the lab frame. So you see that if you have, for example, lots of PEG, you have a large acting polarization, but relatively small, large acting slip speed, but relatively small speed of the cell on the substrate.
Then what the slip speed is as opposed to the
Yeah,
normal
so-
speed. But
Yeah, I can show you this.
for 37,
Yes.
the two bars
Yeah.
overlap, so does this mean that
There was zero split. So in this case, it was zero split. So every actin that was forming in the front was basically immediately stuck there. Okay, so in this system, basically all you see is that actin is polymerizing, and but wherever it is, it's immediately glued to the substrate. So in
does
the
it mean that flow velocity is equal to cell velocity?
in this case, it's equal to polar. Exactly.
Very good. So therefore, actin in the wild type cell actually is static in a lab frame.
Yes, in this case, exactly. For these conditions of substrate.
So is there therefore some other regime, but right, so we can now imagine two regimes.
Yeah.
Kind of static friction
Yeah.
or dynamic,
Yeah. Okay.
and there could be a sort of unsticking transition. And you are assuming that we are in the dynamic friction regime
For the whole cell, yes.
for the whole cell.
Yes.
But curiously, according to this, the wild type seems to be in a static friction.
For the actin filament. So the actin filaments, as soon as they are formed, they are sort of immediately stuck on the substrate. But the whole cell can still move forward. It's not like at all. Yeah. And it also has some effective friction because it is dragging itself on the substrate. Exactly.
I understand.
Okay. This is not actually exactly the case because you actually have to add the two flows together. It's not proportional to each other. But
Wait, so
Yeah.
then I don't know.
no, because
I would have loved to see some ratio of the two velocities, d flow over d cell as a function of something.
yes,
And then the question is, presumably, d flow over d cell is bigger or equal than one. And then the question is there some sort of a stick slip?
so in this model that we had at that time, we didn't have any sticks. So basically, all we had is basically just to add this.
The
Yeah.
question is in the experiment.
Yeah.
Whether there is such a thing,
Yeah,
that's my question.
yeah. So let's
I got it.
yeah.
Absolutely.
Yeah. So in this model, we have the sink because now we really take care of the bonds at the back, which undergo this slip behavior because of the force which is applied on them. And we now do a real force balance for the whole optic. In that paper, in the cell paper, there was no real force balance in that paper. We just dealt with what's happening inside the cell and how is all of that flow translated into moving the cell in the lab frame. We didn't do it. In essence, we didn't do it. Yeah.
Okay, shall we continue these discussions?
Yeah.
It's already been
My
15
pleasure.
minutes, so, but thank Nir once again for a very exciting talk.
Thank you.